Hi everyone, welcome back. If you want to support me in what I'm doing, please press like and subscribe. What happens when you're differentiating and it doesn't say y equals, or it doesn't have to be y, it can be other letters, but in this case here, to make that x equals, make it y equals is a bit more challenging, but we can do it. So I'm going to do one of those to start with and go through it, because there's times when you need to do this. We have a y here and a y there, and I always talk about my equals off times 1. And we're not looking at make this equal to 0, we're not factorising at the moment, we're not solving the equation at the moment, we're differentiating. So what's going to happen with this f? We're going to factorise somewhere. So what we need is we need to get those two y's out. So if I wrote that as y outside of x plus 2, I've changed the two y's back to 1y, which is one of the purposes for factorisation. And then I've got the 5x here as a separate term, and I've got the 3 over here as a separate term. So now I can make that y the subject. So first of all, if I take it slow, I've got y equals x plus 2, and over here I'll have the 3, subtract the 5x. Now before I forget, when it's written here as a y equals, we call it explicit, so it's explicit differentiation. But if we try to differentiate it in this form, that's called implicit, almost like implied differentiation, implicit. So if I divide this side by x plus 2, divide that side by x plus 2, and now I can go ahead and differentiate it. I can call that u, and I can call that v, and I can differentiate the question. So on this one I didn't need a new method, I just needed to rearrange the equation in a different form. But what happens when you can't rearrange the question in a different form? I'll just write up one of those at the moment. So in this question I've tried to look at all the possibilities. If you look up here, I've got something with x, something with more complicated y, a combination of x and y, and one often mucks people up for some reason, just the y by itself, and then just a number by itself. So hopefully they're all in one case without being too complicated. Now anywhere on any equation, I can just simply get the derivative of each term. Now we're looking at terms as being separated by addition, subtraction, or by equals. So I can just write the derivative. I want to differentiate that. I'll try to make enough room. And then I'm going to differentiate that. I'm going to leave a bit of room there too. I'm going to differentiate that. I'm going to have a look at what happens to that in a moment. It's going to be more complicated. I'm going to differentiate that. I only need a little bit of room for that one. And I'm going to differentiate the 10. So anywhere that I want to, I can just add in, including derivative of each term. So this one's nice and easy. We know how to differentiate 2x cubed. So that's just going to be 3 2s are 6x squared. So we've got a nice 6x squared over here. But here I've got a problem. We're wanting to differentiate with the letter y, but we're using the letter x. And I go back to this equals off times 1 again, and we're back to the times by 1. People will say that you're not really timesing by 1, but in practical terms we are. If I write a dy by dy there, what I'm actually doing is I'm putting in a times by 1. A lot of times we don't write multiplication with the derivatives because they're actually the limit. The limit as it's getting closer and closer to a certain point. But for practical purposes, we can just treat it as a fraction. Let's have a look at what we've got here. Now we've got this thing here where I've got a d and a dy. So now I've got a derivative of 4y squared. So if I wanted to and be fussy, I can take my time and write, well, that's the derivative of the 4y squared. So now I'm allowed to differentiate that. So we're talking about the y's and the y's. And then we're left over with this dy dx. So it got us out of trouble. So over here, if I kept going down here, I've got 6x squared. Now I've got the derivative of 4y squared is 8y. So the interesting thing is, when you're differentiating a function in y, or a term in y, is you can just say, what's the derivative of that? This is a shortcut. It's just 8y by dy dx. So we're going to apply that over here in a minute, but we're in a more complicated situation. Let's have a look what's going on here. I can talk about those two there as, go back to this rule here, which is talking about the product rule. So in the middle of one of these, you get a product rule. I was tempted almost to not put it into here and make a separate video, but no, I'm just going to put all in one go. So how are we going to do that? So what we're going to do, I'm going to write it as v u dash plus u v dash. Let's just see what happens with it. So So the derivative of all that there could put brackets around if you wanted to. So what's the rule for the product rule? We write the V first. In my case, I write it as what I call VUV. A lot of people watching might call it VUV or all sorts of things, or V du dx plus u du dx and all the other possibilities. I just stick to VUV. So if you haven't seen that before, that's what I'm doing with it. So I write the V first, which is the y cubed, and then I want to differentiate this one here. But that's okay, because I'm allowed to differentiate 3x and I just get 3. So that was the easy part. Now you can go to u, that's easy again, which we've got the 3x. Now here's the fiddly part, which is like this one over here. We're going to differentiate y cubed. So we're going to differentiate y cubed, where we've got a little bit of a problem. And the problem is really only that you just go 3y squared by dy dx. Now if that hasn't sunk in yet, I find a lot of students this takes a while to sink in. They have to think of it, or maybe it's me as well, because I didn't learn this until recent years. So in that case there, I can put my extra dy in, so I can now deal with y's. So if I come over here to the next line, I've got a 3y cubed, then I've got a 3x, which is that one there, then I've got a dy of y squared, so I'm going to write it in. d dy of y cubed. There's my d dy, circle it again, it's probably better. d dy of y cubed, and I'm left with a dy dx. And the question's almost done. I do want to introduce this bit here though. For some reason people have trouble, I'm not sure, when it just says, it looks like it's just saying dy dx. So let's check and see what it actually is. So I need an extra dy dy. I'm back to the same as what I just did here. I've now got a d dy of y. A d dy of y, and I'm left with a dy dx. Have a look at that in a second. And if I differentiate 10, I just get 0. So, looks long, it does get quick, you do get used to it, but the question's nearly done. So now I've got a 6x squared, I've got an 8y with a dy dx, I've got a 3y cubed, and I go, what have I got here? I've got a 3x with a derivative of y cubed. So that's 3x with a 3y squared. And it's got another dy dx. It's getting a little bit complicated. Look at this one over here. I've got a derivative of y is 1. So I could have written 1. So it just turns out to be dy dx. So when we've got the d dx of y, if we're careful, it's just dy dx anyway. And that's 0. Now I have a problem. I'm back to this one here. I need common factors. And what's my common factor? I've got a dy dx, and a dy dx, and a dy dx. So it's gone a bit crazy. Let's have a look at what we've got. So I've got a 6x squared, and I've got an 8y bracket, and then I've got over here, I've got a 9xy squared. So what I've dealt with here, I've dealt with that one, I've dealt with that one. Now I'm going to do, I've dealt with that one. 9xy squared with a dy dx, and I'm going to have a 1 and all of those with a dy dx. So I've taken out a common factor out of those three. The dy dx has come out, which leaves 1. The dy dx has come out, which leaves that. And the dy dx leaves that one there. And I can't forget about this one here. Plus 3y cubed equals 0. Now if we want to make dy dx a subject, here's the end of the question. So now I put this one over the other side. I've got 6x squared minus 3y cubed. It's getting long-winded. I'll make that the subject, dy dx. I divide both sides by all of that. And I've got this, what looks like it's a revolving thing, but if you have one point to substitute into there, we can get the gradient. If I knew that this went through at a certain point, then I can substitute the x and the y values in, and I can get the gradient of that equation. And who knows what it is. I haven't even found out or looked up what it is myself. But you can just get the gradient of that equation by substituting the values in there. And that is implicit differentiation. You can imagine how crazy it goes. I do have another video already uploaded where it goes into logarithms. Some people may not have dealt with how to differentiate natural logs as yet. Probably self-explanatory when you watch the video. So yeah, it gets pretty crazy. Hopefully most of the time it's not as crazy as this. Can you imagine as well if you had square roots in there or chain rules within it? You can go all sorts of things. Exponentials, trigonometry, everything can come into this topic. I hope it helps. If you're enjoying it, please just let your friends know.